many different substances in this world, and they all behave differently. These are chemical reactions in which atoms are rearranged in different combinations. Atoms have a positively charged nucleus surrounded by a cloud of moving electrons. Hydrogen has one positively charged proton in its nucleus and one electron forming the cloud. Carbon has 6 protons in its nucleus and is surrounded by a cloud of 6 electrons. Uranium has 92 protons in its nucleus and is surrounded by a cloud of 92 electrons. For simplicity, we usually show snapshots of the electrons. The electrons are arranged in shells, and each shell has room for a certain number of electrons. 2 electrons in the first shell, 8 for the second, 18 for the third, and 32 for the fourth. The electrostatic forces and the distances result in greatest stability when there are 8 electrons in the outer shell. If an atom with 1 electron in the outer shell is close to another atom with 7 in the outer shell, then the forces would result in the electron-changing atoms. This is a chemical reaction. These atoms have now become charged ions and attract each other with ionic bonds. Hydrogen has room for 2 electrons, and to complete its outer shell will share its electron with another hydrogen. This binds the atoms together into a molecule. This is called a covalent bond. The shared electrons are not locked in one place, they are moving around in a cloud. Chlorine has 7 electrons in its outer shell, with room for 1 more. It will share an electron with another chlorine to form a molecule. It is a covalent bond. The electrons are shared evenly between the 2 atoms. Oxygen has in its outer shell 6 electrons with room for 2 more. It can fill its shell by sharing 2. It forms an oxygen molecule with covalent bonds. Nitrogen shares 3 electrons to complete its outer shell. Again, covalent bonds hold a nitrogen molecule together. The inert or noble gases all have full outer shells of 8 electrons and will not combine with other atoms. These are the atoms of fluorine, chlorine, bromine, and iodine. Each of them has room for 1 more electron. As well as sharing, they can steal an electron off another atom. As we have seen, chlorine can steal an electron off sodium. The electron clouds change size, and the atoms become charged ions. Fluorine is the most reactive halogen. It has the smallest atom and the greatest attraction for electrons. The larger atoms attract electrons more weakly, so are less reactive. On the other end of the periodic table, it is the reverse. The alkali metal atoms have 1 electron in the outer shell and can easily lose it. They react by having an electron stolen from them. Lithium, sodium, potassium, rubidium, cesium. The further away the electron is, the weaker it is held. Cesium is the most reactive because it loses electrons most easily. Carbon is midway between atoms that steal electrons and those that have them stolen. 4 electrons is too much to steal or have stolen. So in order to complete its shell, it tends to share electrons. It can share electrons with itself to form a diamond. The bonds are spread evenly around the atom, producing a tetrahedral structure that is very rigid, producing a very hard crystal. In fact, diamond is the hardest substance known. It is a crystal. It is not a molecule. For shorthand convenience, we often draw the stick model to make it easier to see the bonds. Actually, the clouds overlap as they share electrons. Most of our pictures of the atoms are modified for convenience. Carbon can also form graphite. A flat sheet of 6 carbon rings, a polymer of benzene, is one way to look at it. In tension, graphite is as strong as diamond. The bonds are unusual, with 3 of the 4 electrons shared and the 4th electron contributing to a cloud of electrons above and below each sheet. These electrons are free to move and can conduct electricity and heat. The sheets are held together by weak forces, which is why graphite is soft and slippery. Let's now react chlorine with some of the elements of the 3rd row of the periodic table. This is sodium combining with liquid chlorine. It is being heated by a Bunsen flame. The reaction forms a protective coating of sodium chloride crystal on the surface. This stops the reaction. Then the flame outside the test tube melts the sodium, exposing the new surface to more chlorine. The ensuing reaction vaporizes some sodium and it catches fire. Sodium is burning in chlorine rather than oxygen. This is magnesium heated with chlorine. Both these reactions give off a lot of heat. Sulfur with liquid chlorine. With heating, it produces a brown, oily liquid of sulfur chloride. In the first reaction, the electron was completely removed from the sodium to produce an ionic bond. Magnesium would be the same, but with 2 electrons. No molecule is formed. They are now separate ions, each with an electrostatic charge. Each ion will attract oppositely charged ions in all directions. They will form a crystal held in place with ionic bonds. Chlorine with chlorine is a covalent bond. The electrons are shared evenly between the 2 atoms. However, in most covalent molecules with different atoms, the electron is going to be more on one side than the other. In bromine chloride, for example, the electron is pulled slightly towards the chlorine. A bond need not be totally covalent. It may be only 70% covalent, the rest ionic. This will produce a polar molecule with an opposite charge at each end. It will attract other molecules and liquefy more easily than a single molecule. Sulfur would like 2 more electrons, so shares the electrons with chlorine. However, chlorine attracts electrons more strongly than sulfur, so the electrons will spend more time with chlorine than sulfur. There will be more charge on one side of the molecule than the other, so it has electrostatic poles. It is a polar molecule. The molecules will now have a weak attraction for each other and liquefy, producing an oily liquid rather than a gas. On the left-hand side of the periodic table are the metals. They have only 1, 2 or 3 electrons in the outermost shell or energy level. In metals, the electrons are free to move about. The metal atoms virtually become positive ions and are attracted to the electrons between them. The electrons are like a gas that fills the spaces between the atomic ions, holding them together. All metals are shiny. Most look silver because they reflect all wavelengths. The photons, or lumps of light, hit the free-floating electrons, which vibrate, producing a matching photon we see as a reflection. Electrons move fast and carry large amounts of kinetic energy. This is how heat is conducted from a hot spot to cooler regions. It would be more random than this. The free electrons make metals good conductors of heat and electricity. The only exception is diamond, a good conductor of heat, but not electricity. The electron blanket allows the metal to be worked into different shapes. If the electrons were fixed in position, the metal would not yield as easily as this. Under a load, the ocean of electrons can move easily, allowing the atoms to rearrange themselves. To prevent the atoms moving as easily, different sized atoms can be added to hold the layers in place. This way, iron can be strengthened by adding carbon to produce steel. Metals can be made more rigid by alloying with elements from the middle of the periodic table. A bronze cannon is made of copper and tin. Let's see how water dissolves salts by breaking their ionic bonds. Water is an oxygen atom sharing 2 electrons with 2 hydrogen atoms. It is a bent or boomerang shape because the other electron pairs occupy their places too. The electrons are pulled more towards the oxygen, so the oxygen end will be negative and the hydrogen end will be positive. Water has charged poles, so it is polar. When it approaches a salt crystal, the charged ends are attracted to the ions. With room for 6 water molecules around each sodium ion, there is a lot of dilution of the charge, so the bond with the rest of the crystal is no longer as strong. The moment there is enough vibration due to heat, the bond will break and the salt will dissolve. Sometimes the conditions are right for a crystal to form. This is a repeating pattern made of atoms, ions or molecules. There are several ways this can happen. All ions form crystals simply because they attract in all directions. Their size differences dictate the face angles. Crystals are possible with any type of bond: ionic, metallic, covalent, etc. The strongest crystals are covalently bonded. They are called covalent network solids. There are not many of them. Diamond and silicon both form the same lattice structure. Silicon dioxide is a covalent network solid, as is silicon carbide. We've seen that apart from noble gases, every atom can be bonded into molecules or crystals. In the next video, we will see how the bonding between molecules causes solids, liquids, and gases.